So here, given the graph of the function g as follows. So the question is to find the intervals such that the function g is continuous on that interval. Okay, from the picture here, you'll see that, okay, first we have to find the location where the function is discontinuous. For example, the function is discontinuous when the limit does not exist here. For example, the function is not continuous at 4 here. You'll see that because the limit here does not exist, and the reason for this fact is that the left hand limit is not equal to the right hand limit. The same applies for the point at 6 here and 8 here. Okay, and also if you take a look at okay, probably this is around -3 here. The limit do exist, but the value of the limit is not equal to the value of the function. Okay, it seems like that. So the function is continuous on the interval -6, -3, for example, and then -3 until year 4 and 4, 6 and 6, 8 and 8 until infinity, I suppose. Okay. 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 So that's the how we decide whether the function is continuous or not. Okay. Now let us consider the second problem. Here we have a piecewise defined function. So okay, so the question is to find the constant a such that the given function is continuous at every real number. Of course, in a piecewise defined function here, for example, when x is less than 1, the rule for f of x is 2x plus 3a, and we know that this is a linear function, so the function is always continuous there. And similarly, if x is greater than 1, the rule of the function is ax minus 2, and the function is always continuous there. So to find the constant a here, the key point here to check the continuity of the function f at x equals to 1. Okay, so I will write the so number 18, I suppose. F of x equals to, here is 2x plus 3a if x is less than 1, and x is greater than or equal to 1. The rule of the function is ax minus 2. Ax minus 2 there. Okay, so to check the continuity at x equals to 1, we need to we need to verify that the limit x tends to 1 of f of x equals to f1 here. Okay, and here, of course, okay, of course we can calculate f1. F1 is just simply a minus 2. Just replace. Okay, so I will calculate it. F1. Yes, Anikat and Meredith.
To check the continuity, do we use the left hand limit and right hand limit, sir?
Yes,
Or
you're right. Okay, of course. To check first the existence of the limit, we need to verify that the limit, the left hand limit and the right hand limit are equal. Okay.
okay.
Okay. Of course, first let us calculate f1. F1 equals to a minus 2, and in fact, the value f1 here is equal to the right hand limit. Okay. For example, if I calculate the right hand limit first, x tends to 1 of f of x here. So this is equals to limit x tends to 1 plus of if x is greater than 1, then fx equals to ax minus 2, and the limit here is in fact a minus 2. So we need to check the left hand limit now. Okay, the limit x tends to 1 minus of f of x there, if x is less than 1, so the left hand limit for x is less than 1, then we need to calculate limit x tends to 1 minus of here 2x, what is it? 2x plus 3a. 2x plus 3a. And in this case, we have 2 plus 3a. And of course, in order to have the existence of the limit of the function at 1, then, okay, so I will write the right-hand limit have to be equal to the right-hand limit, the left-hand limit. Okay, and the right-hand limit is a minus 2. The right-hand limit is 2 plus 3a. So in this case, I will have 2a equals to minus 4. So a equals to minus 2. Okay. So the answer will be a equals to minus 2 there. Okay. Okay, so let us just to save the time, let us see number 18b. Actually, the idea is almost the same, but now we need to calculate, or we need to check the existence of the limit at 3. Okay, so the left hand limit gives us 2x squared plus a, so 2 times 3 squared plus a, that will be 18 plus a, and then the right hand limit gives us a square 3a squared plus 4. So we need to solve the equation 18 plus a equals to 3a squared plus 4 to obtain a. And then, of course, we need to calculate f3 there. Yeah. And in fact, f3 equals to the right-hand limit. Okay. Okay. So number 19, actually, number 19 is your homework, of course. Here we need to check we need to guarantee that the function g here is continuous. Sorry, probably the continuous word is missing here. So here should include continuous everywhere. So in order to guarantee the continuity for all real number, then we need to check the continuity at 0, and the continuity at t equals to 0, and the continuity at, sorry, should be t equals to 2 there. Okay. Okay, so I will give you a hint. Of course, the detail should be written in your homework. So I will just highlight the idea here. So let us first define g of t equals to c minus cosine of t over t when t is less than or equal to 0, and a t square minus t plus b there. Sorry, plus 2b here. 2b when t is greater than 0, but t is less than 2. And then, okay. Oops. When t is greater than or equal to is a linear function, t plus a plus b plus c, when t is greater than 2. Of course, here, the important point here is first we need to find the value of c here, because here you see that oops, probably, sorry, should be a mistake because at 0 t is undefined. So okay, so I will erase this and then redefine this. Okay, please take a look at this is the correct one. Because c minus cosine of t over t is undefined at 0. But okay, I will take a look at when t equals to 0 in this one. Okay. Anyway, first we need to find the left hand limit first. Okay. So in this case, limit t tends to 0 minus of g of t equals to limit t tends to 0 from the left of c minus cosine of t divided by t. And in this case, if t tends to 0 from the left and the limit exists here, so you'll see that okay, so you'll see that here I have to compare this with the right hand limit, of course. And before that, to guarantee the existence for this, since the denominator tends to 0, then I need to guarantee that limit t tends to 0 minus of c minus cosine of t, and this one should be 0. Okay. In other words, if the last limit is not 0, then the left hand limit does not exist. Okay, so that's why if I calculate this becomes c minus limit t tends to 0 minus of cosine of t equals to 0. So that would be c minus 1 equals to 0. So c equals to equals to 1. There. Okay. So c equals to 1. And okay, of course, if c equals to 1, here I have to substitute it back to the limit, the left hand limit. T tends to 0 minus of 1 minus cosine of t over t is obviously 0. Yeah. So the conclusion will be, therefore, the left hand limit is 0. T tends to 0 minus g of t equals to 0. Okay, so now we need to find the right hand limit. For the right hand limit is quite straightforward because it's only polynomials. Okay. So the right hand limit, okay, is should be 0, but we can calculate this by calculating t tends to 0 from the right of 80 square minus t plus 2b here, plus 2b. And in this case, should be the limit here is 0. Okay, 0 plus 2b, and the right hand limit is 2b. So we know that the limit itself exists whenever the right hand limit and the left hand limit are equal. Whenever the left hand limit of g of t equals to the right hand limit. Okay, so the left hand limit is 0. Okay, and the right hand limit equals to 2b here. So in this case, the conclusion is b equals to 0. Okay.
No absence. What is this?
Yes, pardon. Pardon. Okay. So here the value of c is 1, the value of b is 0. Now it's okay, so now we need to find the value of a. Okay. C is 1, b is 2, sorry, b is 0, So now we need to find the value of a there. Okay. The value of a, we need to consider the limit at 2 now. Okay. Of course, the right hand limit, t tends to 2 from the right of g of t equals to limit t tends to 2 from the right of t plus a plus b plus c, right? T plus a plus b plus c. Okay. And in this case, this becomes 2 plus a plus b plus c. And we know that a is still unknown. So 2 plus a plus b equals to 0 and c equals to 1. So the right hand limit becomes 3 plus a. And the left hand limit, g of t, okay, if I calculate this, this becomes limit t tends to 2 from the left. G of t is 8t squared minus t plus 2b. 8t squared minus t plus 2b. 2b is, b is actually 0, so 2b is 0. Then I will have this one is 4a minus 2 there. Okay, so once again, in order to have the limit at 2 and continuity at 2, we need to guarantee that the left hand limit equals to the right hand limit. And that will be t tends to 2 minus g t equals to the limit t tends to 2 plus g of t. And the left hand limit is 4a minus 2. And the right hand limit is what is it? 3 plus a. 3 plus a. So I will have a 3a equals to 5 and a equals to 5 over 3. Okay. So the conclusion here, a equals to 5 over 3, b equals to 0, and c equals to 1 there. Okay. Any question or comment so far up to this point?
Sorry, sir. I
Yes.
just want to clarify so that for these types of questions, does that mean that like when it says that it's continuous everywhere, that means that the graph connects all the time, and that just despite being a piecewise function, the right hand limit must be equal to the left hand limit so that it could connect?
Yes. Of
Okay.
course, that's a necessary condition at
Right.
2 and at 0 here. Of course, at other point, this already a continuous function.
Right.
It's already a continuous function.
Thank you very
Okay.
much, sir.
So the problem here, we need to consider the point where it's a piecewise defined function is where the candidate of discontinuity will be the point at for this case at 0 and at 2 here, because at any other point the function is already continuous. Okay, so that's the roughly the idea. Of course, in this case, actually the left hand, the right hand limit, the right. Oh, okay. In this case, actually the right hand limit at 0 coincides with the value of the function at 0. Okay, actually, this one is exactly g0. Okay, so and also the left hand limit at 2 coincide with g of 2. Okay. And yeah, actually you do not only checking the left hand and the right hand limit, actually we need to check the value of the function at 2. But the value of the function at 2 here at 0 coincide with one of the right hand limit or the left hand limit. Okay, so in this case we get already the answer here. Okay, so where is the? Okay, now let us consider the equation about the use of the intermediate value theorem, especially for number 20 and 21 there. So in this case, okay, for example, number 20, given the this one is an equation, and in fact, this is the equation x to the power of 5 minus 10 x cubed plus 8 equals to 0. Then we need to verify that the equation has a solution, at least has a solution on the interval 0, 1. Okay, that's the claim. And to prove this, okay, so what is the number? 20. So number 20. So given the equation x to the power of 5 minus 10 x cubed plus 8 equals to 0. So the first step will be to define the continuous function, and in this case, the continuous function is fx equals to x to the power of 5 minus 10 x cubed plus 8. Okay, and in this case, the function is continuous on the interval 0 and 1. In fact, this function is continuous everywhere, but we only take a look at, okay, our focus is on the interval 0, 1. Okay, so the function f is continuous at x equals to 0. Sorry, at on the interval 0, 1. Okay, and then we need to check the value of the function at 0, and the value of the function at 1 is the sign are different. Okay, more precisely, since f0 multiplied by f1. Okay, so to check that f0 and f1 have different signs. One of them is positive, and another one is positive and negative, negative or positive. Then it's simply to check the product of these two functions at 0 and 1. And in this case, f0 is 8. f1 is 1 minus 10 plus 8. So 9 minus 10 is minus 1. So 8 times minus 1 is minus 8, and it's negative. Therefore, by the intermediate value theorem, there is C in the open interval 0, 1, such that fc equals to 0. Okay, and fc equals to 0 means c to the power of 5 minus 10 c cubed plus 8 equals to 0. Okay, therefore c is a solution, okay, to the equation x to the power 5 minus 10 x cubed plus 8 equals to 0 on the interval 0, 1. Yeah. Okay, so this is the interval there. Okay, so that's the solution to this one. Okay, so the next one, probably I will only discuss number 21. Okay, and okay, so actually we are given the equation 21. The equation is to find the solution of cosine of x equals to 5x minus 1. 5x minus 1. Okay. So the idea is that, okay, to rewrite the equation in terms of, let's say, cosine of x minus 5x plus 1 equals to 0. And then we need to guarantee the existence of the solution of this equation on the interval 0, pi over 2. Okay. So obviously, the function here, f of x here, let f of x equals to cosine of x minus 5x. Where is the? I missed the 5x plus 1. Okay. Okay, 5x minus 1 or plus 1? Minus 1. So minus 5x plus 1. Okay. All right. Okay, this is the function. And we know that this function is the sum of cosine function and the linear function. Okay. Minus 5x plus 1 is a linear function. Obviously, this function is continuous on the interval. The function f is continuous on the interval 0, pi over 2. Okay. And then once again, we need to check the difference of the sign at 0 and pi over 2. So since we calculate f0 multiplied by f pi over 2, f0 is 1 minus 0 plus 1 there. And this equals, oops, this, okay, I will calculate it one by one because it's quite long. F0 is cosine 0 is 1 minus 5 times 0 is 0 plus 1 equals to 2. And f pi over 2 is cosine pi over 2 is 0 and minus 5 pi over 2 minus 5 pi over 2 plus 1. And obviously, if I rewrite this as 2 minus 5 pi, okay, approximately pi is 3.14 multiplied by 5 is approximately 15. 2 minus approximately 15 is always negative here. Okay, f2 is positive, f pi over 2 is negative. So by the intermediate value theorem, the value theorem, there is c in between 0 and pi over 2, not including both, such that fc equals to 0. And fc equals to 0 means just replacing x by c. Then we have cosine c minus 5c plus 1 equals to 0. And then we can rewrite this as cosine of c equals to 5c minus 1. Okay. Therefore, we have proof that there is a number c in between 0 and pi over 2 such that this c is a solution to the equation cosine of c equals to 5c minus 1. Okay. And we are done. All right. Okay. So, any question or comment so far up to this point? All right. Okay. So, meeting audio. Can you hear my voice now?
Yes, sir.
Okay. Good. So, that's the about the intermediate value theorem. Now we'll continue to the next discussion about the derivatives. Okay. Okay. First, let us consider the concept review. Okay. For the concept review here, 1A. Okay, we'll read it first. The gradient of the tangent line to the graph of the function f at the point c comma fc is simply just using the definition of the derivative here. So, okay. So we continue to the tutorial chapter 2. 1A. Here I will have the gradient of the tangent line at the point c comma fc is limit h tends to 0 of fc plus h minus f of c divided by h, and that will be the answer here. Okay, and okay, I will continue to the okay. For 1b, the equation is the instantaneous velocity of the particles motion along a line at the time c is the limit of in the time interval between c and c plus h as h approaches 0. So the answer here, we recall that the instantaneous velocity is actually the limit of the average velocity. Okay, so the answer will be 1b is the average velocity. Okay, for 1c, okay, I will go on to this one. So 1c, the derivative of f at x equals to a, if it exists, is defined by f prime of a. And once again, we only just write the definition of the derivative at the point a. Okay, and in this case, f prime of a equals to the limit x tends to a of fx minus fa divided by x min a. Of course, you may write it in a different way as f prime of a is also equals to the limit h tends to 0 of fa plus h minus fa divided by h. This is the same answer. Okay. Okay, so now okay, 1D, sorry, yes, 1D. 1D here, an example of of the function f of x, which is continuous at x equals to 0, but f prime 0 does not exist is, okay, so the question is to ask what is the function f such that f is not differentiable at 0. Okay, and the answer will be one of the answer. Of course, there are many answers. The easiest one will be fx equals to absolute value of x. Okay, so f of x 1D, f of x equals to absolute value of x is not differentiable at x equals to 0. At
Sorry.
x, yes,
Would
yes.
would the natural log of x also be an example of such function?
Natural logarithm, we haven't studied the natural
Oh,
logarithm,
okay.
and of course natural logarithm of x is undefined at 0. The question is here we want to have the function f that is defined at 0, but it's not differentiable.
Oh, okay.
We haven't discussed natural logarithm because It's a transcendental function. We'll discuss it in the end of this semester. Okay. To find the counterexample like this, we need to take a look at the easiest example. Okay. And absolute value of x is obviously the candidate, because the reason of this is because the limit x tends to 0 of f of x minus f0 divided by x minus 0 is the limit x tends to 0 of absolute value of x minus 0 over x here does not exist. And the reason of non-existence of this is the left hand limit and the right hand limit is not equal. Okay, that's the reason. Okay, the reason is if I calculate the left hand limit of absolute value of x over x, is left hand limit is minus x over x, and that will be the left hand limit minus 1. That will be minus 1. On the other hand, the right hand limit x tends to 0 plus x over x, limit x tends to 0 plus of 1, that will be 1. You'll see that the left hand limit is minus 1 and the right hand limit is 1. Okay. 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 The last one for the concept review is one is just the product rule and the quotient rule. Okay, just recalling the product rule and the quotient rule. Okay, so let us write it. E given px is the product of fx and gx, and qx is just the ratio of fx and gx. First, we work on p prime of x, and recall that the derivative of f times g is not equal to the derivative of f times the derivative of g. And in fact, this one is f prime of x gx plus fx g prime of x. Okay. Okay. And the next one, if okay, if qx is f of x, qx is f of x divided by g of x, then q prime of x equals to g of x squared f prime x gx minus fx g prime of x. Okay, that will be the for q. Okay, so the last one, okay, I will write this immediately here just to recall that what is the derivative of sine of x, and the derivative of sine of x is cosine of x. And then the second one, what is the derivative of cosine of x, and that will be, do not forget, minus sine x. Okay, that will be the derivative. Okay, right now okay, so for number 2 and 3 here, okay, for number 2 and 3 here, the idea is that we want to find what is the derivative of the function by using the definition of derivative. Okay, of course, for 2a, okay, and let's say 3b as well as 3a is quite similar, and 2b is quite straightforward. Okay, so probably the okay, I will just discuss 3c is quite delicate there, because there is square root of x there. In fact, square root of 3x plus 5. Okay, so now let us calculate it. 3c here. Okay, so for 3c, f of x equals to square root of 3x plus 5 there. So I want to know what is the derivative of f prime of x here equals to the limit of, it's better to consider this type of limit h tends to 0 of f at x plus h minus f of x divided by h. And the limit becomes limit h tends to 0 of square root of 3 in the bracket x plus h plus 5 minus square root of 3x plus 5 there divided by h. Of course, I can expand the last term by limit h tends to 0 of h square root of 3x plus 3h plus 5. And then subtract this h by minus square root of 3x plus 5. And that, okay, so the idea is to, in some sense, we multiply it by the conjugate. Okay, the conjugate means, okay, it's quite long. Okay, I will write it here. F prime of x equals to the limit h tends to 0. Okay, square root of 3x plus 3h plus 5 minus square root of 3x plus 5 over h, and then multiply by the conjugate of the square root. Conjugate means if I have square root of a minus square root of b, let's say its conjugate is square root of a plus square root of b. That will be square root of 3x plus 3h plus 5 plus square root of 3x plus 5 divided by square root of 3x plus 3h plus 5 plus square root of 3x plus 5. Okay, so multiplying this, we will have limit h tends to 0, and we have 3x plus 3h plus 5 minus 3x plus 5 itself, and we have h multiplied by this square root of 3x plus h plus 5 plus square root of 3x plus 5 there. Okay, actually, for the numerator, we'll have 3h there. Okay, so 3h divided by h, we get limit h tends to 0 of 3 square root of 3x plus h plus 5 plus square root of 3x plus 5. And okay, just using the limit theorem now, as h tends to 0, we have this one is 3 over 2 square root of 3x plus 5. Okay, so that will be the derivative. Of course, later on, we can learn, okay, when we are dealing with the implicit differentiation, we can learn the derivative of, let's say the power rule for the derivative, but the power is a rational number. Okay, and the rule is certainly similar to the power rule where the power is an integer. Okay, so later on, if we consider the the implicit differentiation, if I have y equals to x to the power r, then the implicit differentiation say that dy, okay, dy dx equals to r x to the power r minus 1. Okay. Okay. So, okay. So I will just give the overview for another part. For number 4 is actually the reverse of number 3 and 2. So given the limit, then we need to find what is the function and what is the point where the derivative of the function at that point is just the given limit. And number 5 is actually the interpretation of the derivative as the instantaneous velocity. Okay. And number 6 here is the interpretation of the derivative of as the gradient of the tangent line. The same applies for 7. Okay. And 8 as well. But 8 here, okay, of course, the derivative does not exist where the function is not continuous. So again, just take a look at the point where the function is discontinuous, then it implies that the function is not differentiable at that point. Okay. Okay, and number 9 is the once again considering the left hand and the right hand limit in the definition of the derivative. Of course, you may take a look at the graph of the function as well to indicate where the function fails to be differentiable. And number 10 is to consider the graph of the function, its derivative and its second derivative. And number 11 is actually almost similar to the one in the continuity. Okay. Number 12 is just the application of the product rule and quotient rule. Same applies for 13, is a rule for finding derivative. And number 14 is the derivative of trigonometric function. And number 15 is just the derivative of trigonometric function, but we need to elaborate it with the trigonometric identities. And 16, the equation of the tangent line. The same applies for 17. 18 is the interpretation of the derivative as velocity. Same applies for 19 is the gradient. And okay, number 20. Yeah. Oh, okay. Number 20 here, you'll see that although absolute value of x is not differentiable, but we can find a function g such that its derivative is absolute value of x. As in fact, that function is x multiplied by absolute value of x divided by 2. Okay. Okay, so probably that's all for the highlight of the chapter. So please first do it by yourself first, and then I will discuss this in the next lecture on the next tutorial. Okay. And okay, so that's for chapter 2 part 1. Okay. Of course, there will be a chapter 2 part 2, but of course, you still have time to complete the. So I will also later on will give you the homework related to this one. Okay. So please do it by yourself first, then we'll discuss it later on. Okay. I guess that's all for today.